Work is a doorway into energy. We're going to define work. You all know about work. We do work all the time. We're going to give a specific definition to work. And this definition says that unless something is actually moving, then you're not doing any work. So those that just sit at their desk, by the physics definition, aren't doing any work. Like I said, the work is a doorway into energy, and energy is another way of solving problems. And instead of the kinematics, we can actually use conservation of energy to solve many problems. Some of them very complicated, but in a very, the problems themselves are complicated, and if you attacked them using the tools that we've developed so far through chapters 1 through 5, then it's going to be a terrifically difficult problem. But with conservation of energy principles, you can solve them in one line. It's a very powerful mechanism, and it also gives us insights into the world and how it works. So first, the work done by a constant force. Let's just define it. Define the work done on an object by a constant force. If we know all about forces, let's say this is a particular force like gravity or the normal force or some friction, some force. That's the force. And if we call S, this vector, as the displacement vector, we're going to use a little bit different notation in this chapter. And the reason is the notation that we've been using up to now, delta R for the displacement, it's just a lot of writing. You have to write the little delta triangle and then the R. And so it just saves us a little bit of writing, and this is a standard notation for displacement. So S is just a displacement. It points from the initial position to the final position of the object. So we have an initial and a final. Then S, aka delta R, is the displacement vector. It's a vector that points from the initial spot to the final spot. Theta is defined as the angle between F and S, the force and the displacement, when those two vectors are placed tail to tail. And then the work is defined by this equation. And that's the essential piece of this concept. The work done by some force F, and we'll substitute for this subscript the force that we're interested in future examples, and examples in this chapter. The normal force, mg for gravity, etc. That work done is the magnitude of the force F, whatever that is, the magnitude of the displacement. What's that? If you go back to chapter 3, that magnitude of that displacement vector is simply the distance between the initial and the final positions. Distance between the initial and the final positions. And then theta is what we already defined before, the angle between F and S, these two vectors, when they're placed tail to tail. Let's do an example. So this woman is pulling her luggage by its handle. The force that she's exerting on that handle is in the direction shown, and that force makes an angle of theta with the floor. It's directed in an angle theta above the horizontal direction. And if she makes a displacement, if this right tire makes a displacement along the floor, goes a certain distance, the magnitude of that displacement is the distance, then the force that she exerts on this, then the work done by this force on this luggage is Fs cosine theta. So note, well, we'll talk about that a little bit later, but that's the force, or the work. The work is the magnitude of the force the distance traveled, the magnitude of the displacement, times the cosine of the angle in between. We'll talk more about that cosine and what it means. It's interesting to note, and important to note, that this piece of the force, the F cosine theta, so ignoring for the moment this distance s, that F cosine theta piece, well, that's actually the component of the force in the direction of the displacement. All right. So what that says is that what matters in the work is how much of that force is pointing in the direction of the displacement. If it's a lot, the work is going to be big. If it's little, the work is going to be small. Okay, which one of the following combinations of units is equal to the joule? In fact, before we do this question, I'd like to finish this concept, and that is the definition of the unit for the work. The unit is called the joule, named after a physicist that studied work and how it relates to thermodynamics, which we'll talk about later in this chapter. And the joule is defined as a Newton times a meter. Newton times meters. How do we know that? Well, theta has no units. It's the units of radians, and cosine of theta also has no units. So the units in the definition of work are the units of force, that's newtons, times the units of distance, that's meters. So the joule is a Newton times a meter, and that's worth committing to memory. The easiest way to remember it, though, is just to remember this definition of work. Force, magnitude of force, distance traveled, and the units are Newton times meters. That's the joule. This next question is, which of the following combinations of units is equal to the joule? Well, let's take a look. The joule, 1 joule, is 1 Newton meter. But we know what a Newton is. A Newton we can get from force is in newtons equals ma, mass times acceleration. So the Newton is a kilogram for the mass times the acceleration, and what are the units of acceleration? Meters per second squared. So there's the Newton. Here's the meter that came along for the ride. So the units that we're looking at are kilogram meter squared per second squared. Those are the units of joules. Looks like a Newton, except instead of having a meter in the numerator, it's a meter squared. So those are the units, and that looks like the answer. This is the correct answer. Pulling that suitcase. Let's actually do this example now. A woman exerts a pulling force of magnitude 45 newtons. So the magnitude of the force is 45 newtons. And it's in an angle theta equals 50 degrees on a suitcase. Find the work done by the suitcase by the pulling force for a displacement of magnitude 75 meters. So that's the distance. Well, here's the definition. It's the magnitude of the force, magnitude of the displacement, cosine of the angle in between. The force is 45 newtons. Displacement, the distance is 75 meters. Cosine of 50 degrees. That gives us 2,200 joules. So that gives you an idea of, this would be a fairly typical work in the tens or hundreds or thousands of joules. for the typical things that we deal with in everyday life. A weightlifter bench presses a barbell whose weight is 710 newtons, raising it a distance of 0.65 meters and then lowering it back down. So this is the force. The distance traveled is 0.65 meters and then lowering it back down. How much work does he do in raising and lowering the barbell? And we're told that the barbell moves at constant velocity. So let's look at raising first. He's starting down with the barbell here against his chest. It goes up by 0.65 meters. The force he's exerting on that barbell is 710 newtons. So the reason why this constant velocity is pertinent here is that there's two forces on the barbell. There's the force of the weightlifter pushing up on it, that's what we're calling the force F, and the force of gravity pulling down on it. If the velocity is constant during the whole time, then the magnitudes of those two forces would be the same. If it were accelerating, then one would counterbalance the other. So that's why the constant velocity is pertinent, so that we can set this force equal to the weight. Well, let's do the calculation, and this is it. For raising, we want to do Fs cosine theta. Here's F, it's upward. Here's S, it's upward. We need F, that's the magnitude, S is the distance, and we need the angle between F and S. What's the angle between those two when they're placed tail to tail? Well, the answer is, I'm going to take this F and this S, bring them so their tails are together, not head to tail like you do in vector addition, but tail to tail. And the angle between them is 0. They're parallel to each other. So that angle here is 0. The cosine of 0, if you'll recall from your trigonometry, is 1. So multiply the 710 by 0.65, times it by 1, and you get a positive amount of work while he's raising the barbell. So this is a key, and this is a clue. If you can remember what I'm about to say, it'll help you on a lot of different problems. If the force and the displacement are parallel to each other, the work done by that force is positive. And that's what we've said here. When a force is parallel to the displacement, the work done by that particular force is positive. We could have considered the work done by gravity, but we're not. We're considering the work done, in this case, by the force that the weightlifter is exerting on that barbell. All right, so now lowering. He's up here at the top, and he wants to come down, so he's going to bring that bar back down to his chest. The displacement now from the initial position to the final position is down. And the force he's exerting is still up. And you know that because when you're lowering that bar, you're still having to push up on it to avoid it from crashing into your chest. So the only thing that's different now is the angle between F and S. So we got a force F that's up, S that's down. What's the angle between them when they're placed tail to tail? Well, you say it's 180 degrees. And you'd be right. And the cosine of 180, cosine curve starts up like that, comes down like that, and that's the very lowest point. That cosine gives a -1. Cosine of 0 is 1. And that's a great, if those two results are not kind of close to the top of your brain right now, it might be good to review that or just commit them to memory right now. Cosine of 0 is 1, cosine of 180 is -1. So we get a work that is negative. in the case of him lowering the bar. And you say, well, that makes sense to me because he's lowering it rather than raising it. The force and the displacement are opposite to each other. And so that is the second kind of rule of thumb to remember, that if the force and the displacement are opposite to each other, then the work done by that force is negative. That's what we said right here. We've got a force, in this case for raising, the force is parallel to the displacement. For lowering, the force is opposite, in the opposite direction to the displacement. Some of the problems involve calories. And calories are actually related to joules. And here's the conversion factor. There are 2.39 times 10 to the minus 4. You don't have to memorize it. If you need it for a problem, just look it up in the book or find it online or wherever. If you need it on a test, I'll provide it for you. But a kilocalorie is a unit that's much larger. I'm sorry, a joule is much larger. I'm sorry. Yeah, I'm struggling for words here. It takes 1 joule is a very small amount of kilocalories. So actually, if you wanted to get 1 kilocalorie, you'd have to have a lot of joules. So the joule is a smaller unit of measurement than a kilocalorie. Kilocalorie is a lot of energy, a lot of work. So how much work does the lifter do in raising the barbell? We found that it was 460 joules, but we can convert that to kilocalories using this conversion factor. The joules cancel, and we get 0.11 kilocalories. Kilocalories are in the book they're called nutritional calories, and colloquially they're called calories. So when they talk about a 2,000 calorie diet, that's kind of the daily recommended, it's really kilocalories. It's nutritional calories. Okay, there's a conversion factor. Beat that one to death. Let's look at another example, a 120 kilogram crate. So this is a crate that's sitting on a truck. Rests on the bed of a truck, accelerating at 1.5 meters per second squared. So we've got an acceleration here. It says 1.5 meters per second squared. And it goes a distance of 65 meters. The crate does not slip. Even though the driver of the truck is pushing on the accelerator, he's not pushing so hard that it would cause that crate to slip. Find the work done on the crate by each of the forces acting on it. Let's look at the forces on the crate. If this truck is stopped, this is another great example from chapter 4. This truck is stopped and the driver pushes on the accelerator. What force is it that causes the crate to accelerate along with the truck? And you say, well, isn't it static friction? And I say, yes, it is static friction. It's static friction that causes it to accelerate. How so? If there were no friction, if it were on a frictionless surface, then when you accelerated that truck, then the crate would just stay right where it is. The truck would slide out from under the crate, and the crate would fall straight down. So it's the friction that causes it to accelerate. So we're supposed to find the work done on the crate by each of the forces separately acting on the crate. But first, we need to balance out the forces. So what are the forces? We've got static friction force pushing it to the right, because without that it would never go to the right and stay with the truck. We've got a normal force that's holding the crate and stopping it from falling through the bed of the truck, and we've got the weight, mg, acting down. And we want to find the work done by each of those forces. First of all, let's find out what those forces are. If we say this is the x direction, the plus x direction, and we look at the forces in the x direction, then there's only one force in the x direction. It's that static friction force, and it's pointing in the plus x direction. Then over on the right-hand side, we got the mass of the crate, 120 kilograms, and then we've got, there's a typo here that I need to remember to fix on slide 9. This is 1.5 meter per second squared. So the acceleration is 1.5 meter per second squared. So I should have had that parenthesis out there. Either way, multiply the mass by the acceleration to get 180 newtons, and that's our static friction force. Let's find the work done by the static friction force. The work done by static friction equals the magnitude of that force times the displacement times the cosine of the angle between. Here's the force, here's the displacement. So displacement is to the right, force is to the right, bringing their tails together, their angle between them is 0. So that's why this angle is 0. We got the force, the static friction force, its magnitude is 180 newtons. The displacement, or the distance traveled, is 65 meters, and that gives 11,700 newtons as the work done by friction. Now, let's figure out the work done by the normal force. That's this. Work done by the normal force during this displacement, starting here, ending here. Well, it'll be the magnitude of the normal force times the displacement, 65 meters, times the cosine of the angle between the normal force and the displacement. Well, let's have a look. Here's the normal force. It's up. Here's the displacement. It's to the right. What's the angle between this normal force and that displacement? And you say, well, 90 degrees. And I say, yeah, it's 90 degrees. Well, that's kind of embarrassing, because if you remember what the cosine looks like, the cosine is 0 at 90 degrees, it's 1 at 0 degrees, and it's a -1 at 180 degrees. But at 90 degrees, that's the one we're interested in here, it's 0. So the work done by that normal force is 0. We didn't even need to figure out what the normal force was. It wouldn't have been hard, but we didn't need to figure out what it was because the angle was 90 and the cosine was 0. Well, does that make any sense? Well, yes, it does. Because remember when we talked about the work, we talked about the fact that the work done is the component of the force vector in the direction of the displacement. Well, does this force vector have a component in the x direction? You say, well, not really. It doesn't. None of this is pointing in the x direction. It's only pointing in the y direction. So it makes good sense that if those forces are perpendicular to the displacement, then the work done will be 0. And so that's the statement here. Remember we talked about when the force is parallel to the displacement, you get a positive work. When it's opposite the displacement, you get a negative work. And now, when it's perpendicular to the displacement, you get 0 work. All right. What about the work done by gravity? Well, I'll let you do that one. Here's gravity. The weight is equal to m times g. That's the force. The displacement's to the right. What's the angle between them? Well, force, displacement, the angle is 90 degrees, and so we again get 0, which follows the same rule here, because that force is perpendicular to the displacement. So to kind of summarize, this is the definition of work for a general force. If we look at that cosine of theta graph. So this is exactly what I was drawing by hand on the previous slide. If theta is 0, then these two, the force and the displacement, are parallel to each other, and we get a positive amount of work. So we get a positive amount of work for angles between 0 and 90 degrees. At 90 degrees, we get 0 work, and between 90 and 180, we get negative amount of work done. So at 90 degrees, they're perpendicular, and at 180 degrees, the force and the displacement are opposite each other. All right, in which one of the following circumstances does the force do positive work on an object? So this one should be fairly straightforward. The direction of the force is perpendicular to the object's displacement. Well, that can't be true, because when it's perpendicular, you get a 0 amount of work. The direction of the force is in the opposite direction of the object's displacement. Well, that's not true either. You can't get a positive amount of work in that case, because in this case you get a negative. So that's not true. No matter the direction of the force, positive work will be done if there is a displacement of the object. Not true. Depends on the angle. The direction of the force is in the same direction as the object's displacement, and this is the one that we're looking for. The object's displacement is 0 meters as the force is applied. Okay. Model airplane moves with constant speed in a horizontal circle at the end of a guideline. So this man at the center of the circle is not yanking on that cord to get the plane to go around. It has its own motor, and that's pushing it through the air to make it go around. This man or boy or whatever is just holding that, not exerting any force except for the tension in this wire. Well, what's the work done by the tension in the guideline? And when we talk about the work done, we need to talk about the work done on what? And in this particular case, we're talking about the work done on the plane by the tension in the guideline on the plane. So I might ask you, what's the direction of the tension force acting on the plane? Well, it's pulling the plane toward the center of the circle. If it were not so, that plane would just take off and leave the circle forever. So the tension's acting in this direction. The velocity, which is parallel to the displacement at any given time, so it's making little displacements. It makes a displacement here, then a displacement here, then a displacement here, etc. It's making little individual displacements. But how do we compare the direction of that displacement, which is going around the outside of the circle, to the direction of the force that we're trying to calculate the work for? Well, they're perpendicular. That tension is perpendicular to the direction of motion, the displacement of the particle, of the plane. So the work done by the tension in the string is 0. Units for measurement of work, the only ones we'll really be interested in are SI units. Force is in newtons, distance is in meters, the work done is in joules. But just so you know what other systems of units, what units they use, in case you encounter them in whatever context. In CGS units, the force is measured in dynes, the distance measured in centimeters, work done in ergs. British engineering units, force is measured in pounds, distance measured in feet, and foot-pounds is the British engineering unit. You might have heard of that unit before. It's also the unit for torque, pound-feet. We'll talk about that in a later chapter.